This is another classic calculus related rates problem involving an inverted conical cone. Problems similar to this have shown up on the AP exam as well as our own unit test. Let's start by reading and drawing a labeled diagram. First, we're told that a water tank has the shape of an inverted circular cone. So we need an inverted circular cone. Luckily, I have one right here ready to go. Inverted means that the vertex is at the bottom. Okay, next we're told that it has a base radius of 2 meters. So we're going to go ahead and label that radius, which goes right to the middle here, of 2 meters, and it has a height of 4 meters. We're told that water is being pumped into the tank at a rate of 2 cubic meters per minute. Now, when I look at cubic meters, that makes me think of volume. So I now know that dV dt, V because it's cubic meters, and T because it's minutes, minutes being measure of time, equals 2 cubic meters per minute. So the units are really helpful in figuring this out. And next it says find the rate at which the water level is rising. Okay, I need some water in here, so I'm going to use blue to represent my water. So let's put some water in here. So this part that's in blue has water. And I want to know at what rate the water level is rising. So I need a variable to keep track of that. I'm going to use h for the height of the water. So at what rate is the water level rising? That means I'm going to be asked to find dH dt when the water is 3 meters deep. So when h equals 3. All right, usually students find it's pretty clear that we want here a volume formula because we're working with volume and height. And so for a cone, our volume formula is 1/3 pi r squared h. All right, now one might be tempted to just go ahead and take the derivative and hope everything works out. And it is possible to do the problem that way, but I want to demonstrate what happens and why we're not going to choose to do it that way. So on a separate page, don't write this part down, just follow along. We could take the derivative with respect to t. I could keep pi over 3 out front as a constant. I could do r squared times dH dt. So that's r squared left alone, derivative of h, plus the derivative of r squared, 2r dr dt, times h left alone. But the only problem is here is that I have all of these references to dr dt and r, and look at all my stuff over here. I had dV dt, and I had dH dt, and I had h, and no mention of r. So the question is, could I do this without knowing r? So let's go figure that out. So we're back to where you want to be taking notes. And what's going to help us with this is in finding a relationship between h and r is to look at two specific triangles. So when we do this, I'm going to go back and draw out this triangle right here that I have in purple here. And I'm going to drag it off to the side so we can see it more clearly. So there's that triangle. And then I'm going to also copy in blue the triangle for the water. There it is. And we'll bring that one over here. And you should notice that these are similar triangles. You'll recall from geometry they're similar triangles because this angle is the same, and so is this angle. And actually this angle is the same as well. All right, so let's label these. This was 2, and this is 4. And the other one was R and H. And the reason this one is R and H is because the water level's height and radius keep changing, whereas the actual cone is constant. The size of your water cup does not change, but the amount of water in it does. All right, now recall when we're working with special triangles, we just simply make our proportion 2:4 as r is to h. Because in the formula r is what I did not want there, I'm going to solve this one for r. So I'm going to multiply by h, so I get 2/4h, or I can reduce that to h over 2 equals r. All right, so now we can substitute in, and we get volume equals 1/3 pi h over 2 squared times h. And that doesn't look too bad. And you could do product rule with this, and that would not be the way I do it. And I'm going to, again, take you down a path to show you what happens if you do it and why I don't want to do it that way. So we're going to go ahead and we'll come back. But I want to show you if you were to take the derivative at this point, what would it look like? So dv dt, I've got 1/3 pi as my constant out front. And here's my derivative. The derivative of this piece, we might do 2h over 2 times the derivative of the inside, 1/2 times dh dt times h left alone. We're going to have to make some room for ourselves, so we'll just get rid of this right now. And then we're going to have plus, so let's make sure I took the derivative of this. So 2h over 2 raised to the first, derivative of the inside is 1/2, dh dt times that h left alone, plus h over 2 squared times the derivative of h, which is dh dt. It can be done, but boy, we could do it so much nicer. So we're going to go back, and this is where you want to be taking the notes. And I'm going to show you how this problem can look so much nicer, but I'm going to get some of this out of the way first. So that was just our similar triangle stuff. We'll put it out of the way. The key to this being a fairly simple problem is doing some algebra before we even take the derivative. So we'll make this pi over 3. We're going to square this. H squared over 4 times h. Clean it up one more step. Pi over 12 h cubed. And look at that. What a nice equation to take the derivative of. We simply have dv dt equals pi over 4 h squared times dh dt. Isn't that lovely? All right, last step is to plug in the various numbers. We know dv dt is 2. We've got pi over 4. H is 3 squared, and we just want to find dh dt. Last step, we need just a little bit more space here. Oops. And we have dh dt equals, so we've got 2. We're going to have to divide it by the 3 squared, or 9, and multiply it by the reciprocal of pi over 4, or 4 over pi. And we get, that would be 8 over 9 pi. And we should have some units on that answer. So what is h going to be measured in? Let's look at the original problem. We were measuring in meters, and time is going to be in minutes. So it's 8 over 9 pi meters per minute.